Welcome everybody to the MECH 314 Intro to Fluid Mechanics course. Today we are continuing our work on Chapter 4, which is the analysis of fluid flows using the Navier-Stokes equation, which is the differential form of the linear momentum and the mass conservation equations. So here's the parts of the book sections we will be covering for this chapter, and I think we went over those earlier on. Now I would like you to stop this presentation, hit pause, and go watch the video on viscosity that you see in the link over here, because viscosity is an important quantity that we will see quite frequently in this chapter. So please pause here, make sure you watch the video if you haven't watched it already. Even if you haven't watched it recently, please watch it again. So just to say one word, viscosity manifests itself as stickiness. So just like you put honey on the palm of your hand and try to rub your hands, it would feel differently than if you put water. And in a similar manner, even if you try to pull them apart, when you have honey or water, you're going to get a different feel. And that's in a way related to viscosity. It's some measure of viscosity. In chapter 3, we did black box analysis. So all we needed to know is what was happening of our control volume. And we didn't really need to know what was happening inside the control volume. Just by knowing what the fluxes of mass that came in and that left, we could deduce something about the mass that was left in the control volume, as well as if we looked at the fluxes of momentum coming in, the net fluxes of momentum of what came in and what left, we could tell something about the momentum lost or the momentum deficit, which would be accounted for by this external force, which is the weight of the ball. So we could somehow analyze the weight of the ball without even knowing what's going inside this control volume, only by knowing what comes in and by what leaves. So this is great, but if we are interested in knowing what the velocity or the pressure at this point is inside the fluid, and what the velocity or pressure at this point is, then this doesn't help us much. So we need to go into more advanced analysis. Typically, the analysis of chapter 3, black box or control volume analysis, is always a first step, and then once you're done with that first step, you move on. If your answer is not if you don't find what you're looking for, that is, you need more detail, if the answer from chapter 3, control volume analysis, is not sufficient, you move on to do more detailed analysis, which we are going to cover here. So if we want to answer the question, what is happening to the flow right here, what is the velocity in meters per second of the air that's coming out of the hairdryer at this point, we really need to do a differential analysis of this flow using the differential form of the mass and momentum conservation equations. So just to define some terms, in the analysis that we will be seeing, we have a domain. So the domain is the fluid that we have here, which has a density rho and viscosity mu. It's the air inside this region. There is boundaries to the domain, so we define them. So here are our boundaries. So that is what is in touch with the fluid, and which fluid are we talking about? We're talking about the fluid in this red square and outside this ball. So you see, these are the boundaries of the domain. The domain is the fluid that has density rho and viscosity mu. So, and at these boundaries, we set some conditions, and then we will have some differential equations that describe the mass and momentum conservation, and then we will solve these differential equations by integrating them and then applying these boundary conditions, knowing the particular geometry. So you've seen this in your differential equations course. But we're going to go into, even if you don't feel comfortable with your differential equations course, we're going to cover all the material that we need from scratch. So moving on. So the equations of motions that we are going to be dealing with are mass conservation, so mass is not created or destroyed, and momentum conservation, which is Newton's second law. Summation of external forces will be equal to the rate of change of momentum as well as the net fluxes of momentum. So now let's define terms. So we defined a domain. So this was in the previous slide, we defined this as our domain, which actually contains our fluid of density rho and viscosity mu. And next, what we need to do is to define our coordinate system. And our coordinate system, we will be dealing with the Cartesian coordinate system, x, y, and z. So these are the three orthogonal directions. And we have, this would be our independent variables. So they don't vary relative to each other, and they don't vary in space. Our dependent variables would be the velocity of the flow in the x direction, which we call the small u, and the velocity of the flow in the vertical direction, as well as out of the page. So u, v, and w are the three velocity components of the air that's in this domain, in the x, y, and z directions, respectively. Eventually, there is a fourth variable, which is the pressure, as you can see here. And the pressure is our fourth variable. So now we have defined our dependent variables, which are u, v, and w, and pressure. And our independent variables are x, y, z, and obviously we have time. So mass conservation looks like the following. It's the partial u velocity by partial x plus partial v by partial y and partial w by partial z. The summation of those three terms will be equal to 0. The linear momentum conservation, Newton's second law. Newton's second law is a vector equation. So we have our three vector components. We have the x component of the conservation of linear momentum, the y component, and the z component. That's why you see three equations. And you can tell that in the x component, the dominant velocity is the u, just like we have here. So we're primarily concerned with the u velocity, right over here and over there, while in the y direction we're concerned with the v. As you can see, v and v and v and also v, and they have v. And then you guessed it right, that in the z direction we have the w velocity. That's the dominant one that carries the momentum in the z direction. And you can tell, so this is just trying to starting to become familiar with those equations to see what are the variables and what they look like. And here you can see that the pressure gradient in the x direction, the gravity component in the x direction, and that's the y direction, and that's the z direction. So that's a general look at the shape of these equations. So coordinate system is important, that you remember it, that you make note of it. Talking about the fluid domain, defining our terms, and talking about the boundaries of our domain. And then eventually we want to know what the pressure and velocity at this point. We have our equations, we simplify them, then we integrate them, and then we apply our boundary conditions, and then we can find what the velocity and the pressure at this in the whole domain, and then we go to the particular point we're interested in and we find it, and we compute it and evaluate it. Very good. So this is a cleaner slide of so we have boundary conditions, we have a domain, we have our equations. So this is the ingredients of our soup, if you will, for today. And let's start analyzing and dicing and cooking these elements, see where they come from. That we have covered before. I'm not going to cover it again. You look at the previous video. This is a partial differential equation. As we said, it's second order nonlinear because of the nonlinear term. And what we're after is to find the velocity and the pressure at each x, y, z, and t after we solve the partial differential equations. Now let's look a little bit in more the mass conservation and linear momentum conservation describe any type of Newtonian fluid, that is air and water are Newtonian fluids. So let's go back, throw back to our chapter 2, where we had static fluid. And when you have a static fluid, it means that the air or the water is not moving. U is 0, V is 0, and W equals 0. So anywhere you see U, V, or W, U, V, or W in the equations, you set them to 0. That's what we mean by simplifying the equation. So everything with the U cancels out, is 0 actually, in a static fluid. So and there is no gravity in the x direction, no gravitational component. We're picking our gravitational component to be in the z direction. So we're ending up with -1 over rho dp dx is 0. And then we look at the second equation in the y direction. We also get the pressure gradient in the y direction to be 0. And lastly, in the third equation, we have the z component of gravity. So h is the direction in which the gravity is pointing. So in this case, h equals z. So here when we put h, so you put z, dz by dx is 0, and here dz by dy is 0, but dz by dz is 1, so we get the gravitational acceleration right there. So as you see, we relate the gravitational term to the pressure gradient term, and so let's clean those up. dp dx, dp dy is 0, so pressure independent of x and y, and we end up with dp dz to be minus rho g, which is the equation we derived in chapter 2 for static fluids. So we started by assuming we have a static fluid. Excellent. And then how do we get the constant? Is by knowing the pressure at some known, so we have to have some known pressure at some known z, which would be our boundary condition. Typically, maybe the surface of our water bottle where the pressure is atmospheric, or some other point. It doesn't have to be that. And you get the constant, and then you can now you know the pressure at each and every point in the domain x, y, and z. So P is independent of x and y and depends on z linear. Okay, so welcome back. Here is our Navier-Stokes equation, and this is the Navier-Stokes equation for a constant viscosity fluid. So now we'll start talking about viscosity. And constant viscosity fluids cover air and water, which are predominant in engineering applications. So our task now is to derive the Navier-Stokes equation, mass and momentum conservation. So we will start with mass conservation and then move on to the momentum conservation once we get comfortable with the mass. Great, so let's get deriving this equation. Okay, so now we are deriving the equations of motion. So let's emphasize the terms talking about. We have our fluid domain, which is, here's our fluid domain. This is similar to our experiment in class, a hair dryer and a ping pong ball. The fluid domain is where the air is, the air of viscosity mu and density rho. We have our coordinate system x, y, and z, and the three velocity components, orthogonal velocity components of the flow, uv and w. So you want to remember those. And then we have the pressure field inside, the pressure of the air inside the fluid domain. So now let's take a small tiny control volume, dx, dy, dz, dx, dy, dz, very, very tiny. And let's now take, let me change the pin line over here, where x is constant and z is constant, but what is changing is my y. So this is a straight line, supposed to be, where y is varying. And along this line, let me plot some quantity like the horizontal velocity u. And it would, let's say, I'll have some entrainment going in here, and maybe the flow, as it gets closer to the ball, it will move away from it, so I have some component over there. But let me plot the u component as a function of y, and that's what, so now let me flip the picture by 90 degrees. I'm plotting the u velocity that is in centimeters per second versus y along this blue line. And we'll see something like this. It's an arbitrary system. It's an arbitrary plot. Doesn't have to be accurate, but just for demonstration. And just to show you where our control volume is, this dx, dy, dz, on a y plot, we'll be able to see the dy. So this coordinate system is y, and this coordinate system is y plus dy. Those two lines that we have just plotted. And dy is so small, it's very tiny, that over the distance from y to y plus dy, I cannot have an inflection point. So this is what I mean by an inflection point, which means that we're making the assumption that within this control volume, my flow properties could be the velocity u, the velocity component w, or the velocity component v, or even the pressure over this small dy are monotonically increasing or decreasing. So no inflection point. Great. Now that we have got this out of the way, when you have a small tiny control volume, you can predict, or a small distance dy, and your function u, or whatever function you're talking about, is monotonically increasing or decreasing, you can invoke Taylor series expansion, and you can predict what's happening at y plus dy by knowing what's happening at y and by knowing the slope of the curve. So I can write the velocity u at y plus dy it's approximately equal to its value at y, and multiplied plus the little extra term, the slope multiplied by dy. So this we will be using quite a bit. It doesn't have to be u, it could be v, it could be pressure, it could be some other quantity, maybe concentration of smoke in the air, and so on. So now that we have this in our background and in our toolbox, we are going to start the derivation, and we will start with the mass conservation. So remember, we have this is our small tiny box dx, dy, dz. It's in the fluid domain. That's the air that's coming out of the hair dryer and around the ping pong ball. And this is, and if you look at my this tiny little dot, it is a cube. We show our coordinate system x, y, and z, and also our velocity components are uv and w. I can't emphasize this enough. Just want to instill this in you. So you want to remember that this control volume is fixed in place. This is what we call an Eulerian frame of reference. You will see a video link on Moodle that explains the difference between an Eulerian and a Lagrangian frame of reference. Our study in chapter 4 are concerned with an Eulerian frame of reference. So if you encounter the Lagrangian frame of reference, as you will see in the video, that's not what we're talking about. We have our box, our control volume, little tiny dx, dy, dz fixed in space, and the flow is going through it and leaving from it, and from all 6 faces and into and out of the page. And the velocity as it comes in and as it leaves, it varies by a small amount, delta v and delta u and delta w. And those we can, as we have seen in the previous slide, we can relate to the slope of the velocity and the value of the velocity at one point. Very good. The other thing you want to pay attention to is that this is a cube and it has 6 neighbors that are attached to it. It's not sitting on its own. You want to imagine that this in its context, where it is, this is the box, the imaginary box, the dx, dy, dz, sitting among those 6 neighbors, and mass flows coming from one neighbor to our control volume and leaving to another neighbor. It could actually come from this side and leave to the other side, and so on. So now this is our control volume, and we have, as we said, velocities coming in and leaving, and we can use our mass conservation equation for a control volume. This is still a control volume, albeit it's very tiny. The rate of change, this is our equation, the rate of change of mass inside the control volume is equal to the net fluxes of mass in minus out of the control volume. So we will start with the fluxes of mass coming in and out of the control volume. Now let's look at a quantity. Let's look at the mass flow rate coming through the face x, because it's perpendicular to the x direction. So this is the face x that we are talking about, and the area of face x is this distance, which we call dz. That's the area of this face, times dy. And the velocity perpendicular to this area is the velocity u. So if I want to compute the mass flow rate coming into this face, it is the density of the fluid multiplied by the velocity u multiplied by the perpendicular area dy times dz. And now let me take this quantity, rho u, and plug it back into Taylor series expansion. So I can write rho u, so I can predict the quantity rho u at x, so this was at location x. I can predict it at location x plus dx. So at x plus dx, x plus dx, to be the value of rho u at x, which is this guy, plus the slope of rho u with respect to x multiplied by dx. Go back to the previous slide, and that's the equation in red that we had written over there. So now I have my mass flow rate coming in, and there is probably some chain in mass flow rate that leaves from the opposite face along the x axis. So the mass flow rate that leaves is this rho u x plus dx multiplied by the area dy dz, dz. And as you have, we can substitute, as you have seen, we can substitute for rho u at x plus dx with this value. And now let's do this for all other 6 faces, or the rest of the cube, which are on additionally 4 faces. This is the equation that the Taylor series expansion. U here, we looked at rho u, and so you could put in any function that you like, d rho u by dy, which is what we put in the previous slide. Right, so we have 6 faces. Let's do face by face, and we're looking at the fluxes of mass in and out. So let's look at face x. So that's the face perpendicular to the x direction. We have, this is x plus, so here's our x, and here's our face x plus dx. And what's coming through the face x is rho u multiplied by the perpendicular area to the velocity, dy dz, and what leaves is rho u plus some extra change in mass flow from the other face. Now let's look at face y. So the face y has an area dx times dz, so mass flow rate comes at location y, and then leaves from face y plus dy with some tiny change in that mass flow rate. So what comes in this face is rho v dx dz, and leaves with an extra bit, of mass. So this d rho v by dy could be positive or negative. So when I say with an extra bit, that extra bit could be negative. So it could be, doesn't have to be positive. And the slope takes care of that, of d rho v by dy. And same thing we do for the third face. This is the z. So you notice that I'm using the axis to the axis perpendicular to the face to refer to this particular face. So this is the face z, and that's the face z at z plus dz. So here's at face z is the velocity in the z direction, w, multiplied by density, by the area dx dy. And what comes out is the rho w plus this extra bit of mass flow. So here we've done the flux terms, in and out. So it's out minus in, so let's subtract that minus that. And now let's plug in for dv. What is the volume of the controlled volume? Yeah, absolutely. It's dx dy times dz. So let's plug for dv to be dx dy dz. And since it's a small controlled volume, there's nothing to integrate. So the integral sign goes away. It's the same thing. So I get d by dt of rho dx dy dz, which you see right over here. That's the unsteady term. Rho dx dy dz, just because dv is equal the volume of this cube. And now we simplify. Those convective terms that come in and leave cancel out, and we are only left with this extra bit. So you'll see rho u cancels with rho u, and same thing here, and here, and here, and rho w cancel out. So we're left with things that have partial differentials in front of them. And now we clean this up, and we get to our equation. And you'll see every term has a dx dy dz, dx dy dz. So we can divide by dx dy dz, and we end up with the continuity equation that we started with. So by pure magic, we went from a controlled volume into a partial differential equation to describe our mass flow. And let's make life even simpler. Let's say that the density is constant and it doesn't vary with x, y, z, or even with time. So that term goes away. Then the rho, because it's constant, it cancels out, and we end up with the continuity equation, the mass conservation equation that we have seen earlier, du dx, dv dy, and dw times dz. So we will come to this and we will talk about its properties a little bit later on and why it looks like this. Great. So now that we're done with the mass conservation, we derived it. We showed that if we start with a small control volume, we can actually get the continuity equation from basic principles. So we are going to do the same thing, but now let's do momentum. And this is my cube. Remember, so here's the dx, dy, dz, my cube. Again, remember it has 6 other neighbors. We are showing here 4 of them that are easy to draw, and then you want to imagine the other 2 neighbors that are in front of you and that are the one that's hiding behind this red cube. And each one of those cubes is exerting an external force on my control volume, and that force that each one of those cubes is exerting has a direction. It could be in the x direction, it could be in the y or in the z direction. So the summation of external forces will be equal to the mass fluxes, the momentum fluxes out minus n, plus the rate of change of momentum inside my control volume. So it's easy to write the rate of change of momentum just like we did before, and we got rid of the integral sign just because there's nothing to integrate over, because nothing is varying in my control volume. Everything seems, the variation is very, very small, very, very tiny. The other thing to notice that's important in this case is that we have a vector equation. And that vector equation has 3 algebraic components in the 3 Cartesian directions. So this is actually shorthand notation of 3 momentum equations. And if we look at the forces, and now we can, because now we're sort of familiar with the m dot because we derived the mass conservation equation, so we know how to do this. And then all we need is to multiply by v. But the forces that are acting on my control volume, as we said, are the forces from each one of the 6 neighbors on my control volume, plus maybe gravity and some whatever other field. And now let's take face z, which is the y dx, the one that is right in front of us, right over here, this face. And if you see, it has the neighbor to this face exerts 3 orthogonal forces or stresses. And you have 1 normal stress perpendicular to the area and 2 shear stresses. What I would like you to pay attention to, the stress sigma has 2 indices, 2 subscripts. Here it's sigma zy. So the first index, so sigma zy, let's look at this guy here, sigma zy. And what the indices mean, the first index refers to the face z, and the second index refers to the direction of the stress. In this case, it's pointing upwards. So you can guess here, sigma zx, it's the stress on face z in the x direction because it's pointing in the x direction. So you get that. So here's what we just said. So each one of those 6 faces would have 3 stresses on it that we will come to later. And the stresses in a similar fashion, the stress is one property of the flow, so I can predict the stress. If I know what the stress at location x, I can predict the stress at location x plus dx through the Taylor series expansion. But now let's look at the momentum fluxes. So the momentum flux that comes through face x is the mass flow, so it's the area dy dz multiplied by the m dot, rho u dy dz is my m dot, and then I have the v, so m dot times v. I've done that at the inlet, and what leaves is I have my function rho uv So let me take it as just as a function, or if you will, you can substitute for capital V with just U, because we're here, we're looking at the momentum in the x direction. So we come in with a momentum rho uv times the area, and we leave with a new level of momentum rho uv plus this extra bit of change in momentum times dy dz. Just like so this is very similar to what we have done previously. So now let's look at the right-hand side of the equation. So let's hide out the left-hand side, the forces. We'll come to them a little bit later on, and let's do the momentum fluxes. This guy, the unsteady term, is straightforward. There's nothing to do about it. So it just sits where it is. And now let's do the momentum fluxes m dot v at the out minus the in. So let's see what's going into my control volume. So at face x, right? So we're looking in the x direction, momentum in the x direction, which is also face x, dy dz. That's the momentum rho uv. As I said here, you can for v you can substitute u. But we'll come to this in a second. And what leaves is this rho uv plus this extra term, this little extra change in rho uv at the outlet. And same thing in the y direction, I get rho v times v, and then with some extra bit leaving from the other face, and so on with in the w direction at z and z plus dz. So here we should have substituted for the v arrow with, here we substituted u, here we substitute with small v, and here for this v we'll substitute with w. It's just easier with small w. It's easier for our analysis. We'll do this, but we'll leave it to the last step. So we can do it now. It just will confuse us a little bit more. So let's just keep capital V as in a vector, and then once we clean everything up, we'll have less variables to deal with. So let's stick with one variable instead of dealing with 3 different variables. And then we're doing, so we've done the ins and outs and subtract them from each other. And then we have this last term, the unsteady term over here, dx dy dz. Because dx dy dz are independent of time, the volume of the cube, as we said, we're in an Eulerian frame of reference. The cube is just sitting there, and air from the hairdrying is coming to it from one side and leaving from the other 5 sides, and so on. It could be coming from 2 sides and leaving from the other 4, or coming from 4 sides and leaving from 2. So that depends on that's what the solution will tell us in the end. We can't tell by now, but we can derive the more general form of the equations. So let's add those up as we plug them into the equation on the right hand side of the equation. So plug them all up, and you'll see that all the convective terms will actually cancel out. And now we want to do the same thing for the forces. Let's consider the forces in the x direction. So anything where the second subscript has x, so this is the second subscript, we'll sum all those up. So you'll see I have sigma xx on this face, on the x face. On the top face, on the y face, I have sigma yx, so that has the x direction. We're talking about the x direction. And on the z face, I have a sigma z x, which is this guy right over here, on face z and on face z in the x direction. So we'll sum the sigma xx with the sigma zx and the sigma yx. This is what we end up with. And then we can, let's look at the normal stress here, sigma xx at location x. Now I can predict what my stress at location x plus dx to be, the stress at x plus this extra bit of change d by dx of sigma xx times dx. So stress has units of Pascal. whether it's a shear stress or a normal stress. And when you multiply it by the area A, you're multiplying by meter square. So here we're having units of newtons. So this is Newton's second law. We have to have Newton. And now we sum all the stresses in the x direction. So we're doing the sigma fx's. So we'll do on face x, on face z, right, and on face y. And as we've seen before, these these crossed out terms cancel out. These are the convective terms, we call them. We will come and talk about what we mean by convective. So these are the things that don't change. We don't care about things that don't change. They come in and leave and they don't do anything. We only care about the change itself, and that change itself is what creates these forces on my the internal forces between my fluid elements. And then we do the same thing for the y direction. So the second index is y, sigma zy, and sigma xy, and do it for the z direction. So now we add up all the stresses in the x direction together, in the y direction and the z direction, and you'll see we're left with the ones that have a differential in front of them, the partial derivatives, plus the unsteady, the body force, the gravitational, in this case it's the gravity force. So we do it for the x, y, and z. Great, so now we had our momentum on the left, our summation of forces on the left hand side, and our momentum fluxes and unsteady momentum term on the right hand side, and then we sum the x with the x, so we equate the x to the x, the y to the y, left hand side and right hand side. But just like we've done with mass conservation, each and every term has a dx, dy, dz in it, in both left hand side and right hand side of the equation. So we divide by it and just try and make the equation a little bit clearer and cleaner. And that's what we end up with. Our x momentum equation is the d rho u by dt. So it's starting to look similar to what we started with when we described the Navier-Stokes equation, but not quite. And d rho u by dx and so on. So we have an x moment. So this is these are our accelerations. Here is our stresses, our forces acting on our control volume in the x direction, y direction, and in the z direction. Now let's look at those terms, the stresses. So here we have the velocities u, v, and w, and density. So these are things that we are familiar with, the three velocity components. But here we have stresses, internal stresses between the fluid element, the fluid elements themselves. And we can, for us, we really, as mechanical engineers, as mechanic in the field of mechanics, we have pretty much gotten to the end of our line. We've left things in terms of stress. But if we go one step further, we can actually go to our chemical engineering friends. And these are actually the guys who have created the video that I pointed out at the beginning of this lecture. So please again, go back and look at that video. And what they help us to do is now they can help us write the sigmas, the stress, in terms of the u, v, and w. So now our goal is to get rid of those sigmas and just have u's and v's and w's, the velocities in the flow. And for us, we really need to go and talk to our chemical engineering friends or our rheologists. And these are the guys in the video. So now if you go look at the video, you remember those experiments where you have two concentric cylinders and they have some weight hooked up to one of the cylinders to make it rotate, and that weight is the stress, is the force. So you can, from that weight, you can weight in a pulley, you get you divide by an area of the cylinder, you can get a stress. And the motion of the cylinder gives you the UV and W is the velocity. So you see now you get a feel of what we mean to relate a stress to velocities. Here we're going to refer to those from now on strains or strain rates. Is the change. So for the cylinder itself, it would be a velocity, but for the fluid that is in between those two cylinders, concentric cylinders that are in the video, it is the pulling and pushing and the extension of these fluid elements with respect to time between as they get pulled by the two cylinders. So that's the field of rheology. So we were nice to our chemical engineering friends, so they were very happy to give us a relationship between stress and velocity. And here's what they look like. We have normal stresses on the first line, and we have shear stresses on the second line. So as you can see, remember we said at the beginning that pressure is a normal stress. So now it shows up in our equation. So we have three normal stresses: sigma xx, sigma yy, and sigma zz. So these are the stresses perpendicular to the respective faces. And we'll see that pressure is compressive and perpendicular. Because it's compressive pointing towards the face, it has a negative sign. Because if you take the normal vector to the face, it's pointing outwards, and the pressure is compressive. So we have in each one of those terms, we have a pressure component of the normal stress, and we have a shear component of the a viscous component of the normal stress, just because it has a mu or viscosity in front of it. And we're familiar with the pressure term. The normal stress, as we have talked a minute ago, to explain what it is, you take the honey between your two fingers and try to pull the fingers away from each other, to distance them away from each other. So you move them at a certain velocity w in the z direction, and that's what we mean by a normal stress. We're not rubbing our fingers against each other, we're actually moving them away from each other and trying to pull the gum or the honey or the glue that's between our fingers. So that is the normal stress right over here, normal stress. And then we look at the second line. It has the shear stresses in our equation. So the sigma yx and the sigma xy are related to the u and v and y and x, and also sigma zx. Now, so we have the three shear stresses: sigma yx, sigma zx, and sigma zy, and in fact they're equal in both directions, the zy and the yz, and the xy and the xz, as well as the yx and xy. And now to visualize what this shear stress is about, you want to now take honey between the palms of your hands and try to rub them against each other. And if you replace honey with, let's say, alcohol, you'll see that you're gonna have a different, so you take your hand and rub them against each other, and that's the type of shear stress, just because the motion is parallel to the area. The motion of your hands is parallel to the area while you have honey between the palms of your hands. Okay, so we have to thank our chemical engineering friends very much, because now they gave us those relationships. Let's take them and put them back into our Navier-Stokes equation. And we need to simplify things. So here, after a few steps of simplification, so remember when we looked at our equation, we had, if you go back 2 slides before this one, you had duu and duv. So when you apply the differential operator, it's the first times the derivative of the second plus the second times the derivative of the first. So we'll end up with some some extra terms here and other extra terms on the right hand side. But we're not going to go through that. If you do it, you should be able to retrieve this equation. And this is the equation. If you go back now to the first slide we started with, we actually have derived the Navier-Stokes equation from basic. Let me add, excuse me. We derived the Navier-Stokes equation and we derived the continuity equation. Let me say a few words here. We'll come and expand on those later on. If we look at the units, here I have velocity over time, and velocity over time gives me an acceleration, so it's meter per second square. And so this is one type of, so this is an acceleration. Remember, Newton's second law is force equal mass times acceleration, or force over mass is equal acceleration. So this is the form of the equation. Acceleration on the left hand side is equal to the forces divided by mass. And let's look at the acceleration in more detail. The second term has a u over x, a meter per second divided by meter, so that's 1 over second, and then a meter per second, so that also gives me a meter per second square, just like the but it looks different. It doesn't have time in it. The time comes from the variation of velocity with distance. So on the left hand side we have one term that has time in it and 3 terms that has a velocity times velocity divided by a distance. Both of them are called acceleration. The first one is called, we'll come to this later, it's called local acceleration or time derivative, and the second term is called the convective acceleration, or the derivative moving with the fluid element, just because it's moving with the flow. But for now, these are accelerations. And on the right hand side, we have the gravitational force per unit mass, so the weight per unit mass is just the gravitational vector. We have the pressure gradient force per unit mass, and then because it is, you see the pressure, and here we have viscosity. So these are our viscous stresses, stress forces, or viscous stress gradient forces per unit mass. So you'll see forces are on the right hand side, forces over per mass are on the right hand side, and shear stress is on the left hand side. We can write those equations instead of having to write 3 partial differential equations. We can write them in shorthand vectorial notation. So the acceleration term, this whole term, both the local and convective acceleration, will write it as dv dt. So dv dt has both the local acceleration, the local derivative, or the time derivative, as well as the convective derivative. So that's the operator. Local derivative and convective derivative. Local acceleration, convective acceleration. And that is the total acceleration. It has 2 components. Total acceleration. And then you'll see we have arrows on top of each one of those. So this is the vector notation. That vectorial equation is those 3 equations together. Then we have the gravitational force per unit mass, pressure gradient form. So this is the del operator. Del is the du dx in the I direction, plus is the d by dx of the operand in the x direction, plus the d by dy of the operand of the quantity in the y direction, plus the d by dz of the quantity in the z or k direction. And p is a scalar quantity. And lastly, here we have the Laplacian, and the Laplacian is just this guy, del square by dx square plus del square by dy square and del square by dz square. And you'll see that it repeats in all three equations. And what is different between the two we're talking about here, we're talking about velocity w, w, and w. And here we're talking about v, 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 and here we're talking about u and u and u. So you get the point over here. Now the continuity equation, du dx dv dy plus dw dz, we write it in shorthand vector notation as del dot v. So the del operator, as you know, is d by dx in the I direction. So d by dx in the I direction plus, so that's in the I, plus d by dy in the j, plus d by dz in the k. Okay, this is, it's annoying. All right, and then the velocity v has three components, and we do the dot product of those two. The velocity v is u I plus wj vj, sorry, plus wk. Vj plus w in the k. And when you do a dot product of the del operator, which is on the left hand side, by a dot product with the velocity, the I dot I gives you 1, I dot j gives you 0, and I dot k gives you 0. So I get du dx dv dy plus dw dz, which is this guy. So you can take a pause here and just go for a quick revision of your vector calculus or vector notation. It's very quick, or you can just stick with this. We have it spelled out in the coming few slides. So great, we have derived the Navier-Stokes equation from scratch. Good job, everyone. That's fantastic. So now what we want to do is we want to look a little bit at the continuity equation and see what they actually mean. Let's delve into a little bit more detail into those terms in more detail and what they mean. Very good. So let's do that.